Is one of our basic assumptions about the universe wrong? You have surely heard that the universe is actually expanding much faster than it theoretically should, and that mysterious dark energy is considered to be the driving force behind the accelerated expansion of the cosmos. But now physicist Lucas Lamberser is putting forward the intriguing thesis that this is simply not true and that the expansion of the universe is in fact nothing but an illusion. Instead, the universe is flat and static. But what supports this controversial claim? Can it really be that we have been dramatically mistaken on such a fundamental point? Stay tuned until the end and find out with us. It's well known that our astronomical view of the world has undergone some drastic changes in the past. After all, around 100 years ago, renowned figures such as Albert Einstein were still firmly convinced that the universe was an eternally identical and unchanging construct. In this context, our Milky Way was even thought to be the only galaxy in the entire cosmos. But then came the hour of a certain Edwin Hubble, who dedicated himself to the task of getting to the bottom of the strange spiral nebula in space, and with revolutionary results. After the aspiring astronomer had analyzed a regularly flickering star in one of these nebula, it became clear that it could not possibly be within the Milky Way. But that was just the beginning. At the same time, Hubble also realized that the supposed nebulous structures had been misclassified all along, and that they were, in fact, independent galaxies. And after the boundaries of the known universe had been pushed into unknown realms practically overnight, Hubble set about determining the red shifts of the foreign galaxies and sorting them according to their distance, size, shape, and brightness. In doing so, he again noticed a remarkable pattern. The further away a galaxy is from us, the higher its red shift, or to put it another way, the further away a galaxy is from us, the faster it's moving away from us. It soon became clear that the relationship between red shift and distance could be described by a constant, and that Edwin Hubble was the first scientist to realize that the universe is expanding. A groundbreaking discovery at the time, but one that has long since become part of the basics of astronomy and which also allows us to shed light on the origin of the cosmos. Because if space is constantly expanding, then viewed in reverse, it must once have been much smaller, or rather compressed into a single tiny point. Today, we refer to that tiny point as the original singularity from which space, time, and matter once emerged together in the Big Bang. From then on, our understanding of cosmic development seemed to be set in stone. After all, we had managed to uncover the expansion of the universe and, by implication, calculate back to its beginnings. But the cosmos would not be the cosmos if it did not have a few more mysteries up its sleeve. For researchers in the 1990s, perplexed astronomers were confronted with the realization that the expansion rate of the universe had not slowed down after its rapid beginning, as previously assumed, but had actually increased over the past 6 billion years. But shouldn't the force of gravity have acted as a fundamental brake on the expansion of the universe? How could such a mystery, which in one fell swoop undermined our understanding of the cosmic expansion, be solved? Well, apparently, there must be something out there that counteracts the attraction of gravity, and finally this something was named dark energy. However, the antagonist of gravity also has a huge catch. We neither know what dark energy is nor how it works. How the James Webb Telescope deepened the expansion mystery. Although this mysterious force has not yet been directly detected and we can only draw on theories in this regard, experts assume that it accounts for 70% of the energy density of the universe and is a major driver of its expansion. At the same time, however, we must not forget that despite all the dark energies, the expansion of the cosmos is still overshadowed by gigantic question marks. After all, there are still the impossible discoveries of the James Webb Telescope, which once again shake our understanding of the universe to its very foundations. And while this mainly concerns the very early galaxies, which appear to be much too massive for the time of their formation a few 100 million years after the Big Bang, Webb has recently also contributed to further deepening the cosmic expansion mystery. A fundamental point of this is, namely, the question of how fast the universe is actually expanding. And as briefly mentioned earlier, this pace is indicated by the so-called Hubble constant. But here's the thing. Confusingly, the theoretically predicted value of the Hubble constant simply does not match our real observations in space. According to the standard model, the corresponding value should be 67 kilometers per second per megaparsec, but direct measurements based on supernovae, gravitational lenses, variable stars, and red giants have shown that in reality the Hubble constant is 73 kilometers per second per megaparsec. In order to check the investigations of the past for possible measurement errors, James Webb has re-examined the data of its predecessor Hubble in the course of new observations, and once again proved to us that the universe simply does not do what it should on paper. In fact, the overall result this time also yielded a Hubble constant of 72.6 kilometers per second per megaparsec, and researchers don't know how to explain this drastic deviation. Well, with one exception. The physicist Lucas Lamberser from the University of Geneva presented the controversial theory that the cosmos is not actually expanding at all but is instead standing still. Is the expansion of the cosmos just an illusion? But what on earth prompted this physicist to make this extraordinary assumption? Published in the journal Classical and Quantum Gravity, the lead author can be quoted as follows regarding his hypothesis. In this work, we are taking a new look at the cosmos and its unsolved mysteries by mathematically reformulating the physical laws that govern it. According to Lamberser, the observed red shift of foreign structures can also be explained by the development of particle masses, or in other words, for example, protons and electrons, over time. In the same breath, he replaces the expansion of the universe with a field that permeates spacetime and in which the said particles arise and move. In this context, the cosmological constant is no longer influenced by the expansion of the universe but simply by the mass of the field, and since the field fluctuates, the constant fluctuates as well. Furthermore, the physicist's calculations showed that in this context, the actual data on redshift also matched the theory. And he says, I was surprised that the problem of the cosmological constant seems to simply disappear in this new perspective on the cosmos. At the same time, however, the new approach also seems to provide the answer to other pressing research questions, such as the nature of dark energy and dark matter. The latter also exists only on paper and was postulated to explain the movement of visible matter. In principle, scientists assume that dark matter outweighs ordinary matter by a ratio of 5:1. But since it does not interact with light, we have not been able to detect it directly. However, Lamberser suggested that the fluctuations in the superordinate field could also behave like a so-called axion field, where the word axion refers to hypothetical elementary particles without an electric charge and with zero spin, which are also potential candidates for dark matter. Furthermore, the field fluctuations could also reveal the secret of dark energy. According to him, its effect could be explained by the fact that the particle masses take a different developmental path at a later point in the universe. The physicist notes that in this context, there is simply no need for the existence of dark energy. But how is the rest of the research community reacting to this unorthodox approach? Well, Luz Angela Garcia from the Colombian Universidad ECCI, who was not involved in the research herself, was deeply impressed by Lamberser's new interpretation. She said, "The work is very interesting and provides an unusual result for several problems in cosmology. The theory offers a way out of the current tensions in cosmology." But what does that actually mean in concrete terms? Do we have to turn back the wheel of time by a good 100 years and return to the former idea that the universe is static and unchanging? Well, perhaps we shouldn't be quite so hasty after all. Because alongside her praise, Garcia also urges a healthy dose of skepticism. Specifically, we should treat Lamberser's results with caution, since the theoretical model contains elements that probably cannot be confirmed by real observations, at least not in the foreseeable future, because we simply lack the technical means to do so. And so it happens that we will probably have to be patient for a while before we know whether the field proposed by Lamberser really exists and whether it also behaves like the mysterious axion. But speaking of axion, please join us now and press the thumbs up and subscribe button to never miss a new video from our channel Insane of Curiosity again. We'll see you soon.